Hi everybody, welcome back to Chem 12001, the review session. Let me turn off the music here because I can still hear it. The purpose of the day is to go over any questions you might have for the final, which is tomorrow. And it looks like people are posting questions, so we'll start at the top. I need to scroll this in though. Oh, it's not working. There we go. Okay. So let's see here. So on this first question, cost of a pure metal ore is $4.33. Let me get the other color here. Per kilogram. One volume in cubic centimeters costs $137. So we need to buy $137 worth of stuff. And we know that the density of the ore is 12.8 grams per cubic centimeter. So I start with money, because that's the unit that does not have anything else associated with it. That's just this right here. Here's how much I have. I need to buy some of that. So obviously I can figure out how many kilograms I can buy by using this right here. So it's $4.33 equals a kilogram. And I want to figure out a volume. So I need to figure out a way to get from mass to volume. Well, I have something that does that right here, right? So if I knew how many grams I had, I could figure out cubic centimeters. So we'll just turn kilograms into grams into cubic centimeters. And then we know the rest of these conversions. 1 kilogram is 1,000 grams. And the density was 12.8 grams per cubic centimeter. So now we can do all the conversions. So this would be money per kilogram. So the money will cancel out. And then we got kilograms to grams. And then we got grams to cubic centimeters. Just following the little flow chart that we've made. Just like all these problems that we've been doing. And now we can run the numbers. So there were $4.33 per kilogram. A kilogram is 1,000 grams. And there are 12.8, there we go, grams per cubic centimeter. We'll punch it all in the calculator. And I get 2,470 cubic centimeters for 3 sig figs. So again, to do that type of problem, you have to follow the units. I almost said follow the money, but that doesn't really work. You start with the money because that's the unit that isn't a conversion that's given in that problem. And then from money, you can say, well, I know how many kilograms I can buy with, oh, excuse me, with a certain amount of money. And if you know how many kilograms of something you have, you can eventually get to volume using the density. All right, so next we'll do this chapter 6 one. I think we did this one at the last review, actually. So we got 35.8 grams of whatever this is. Reacted with excess O2, how many grams of CO are produced? Do you have the balanced equation for this? Because I don't have a balanced equation, so I don't know what to do with it. We'll come back to this one. What type of reaction is aluminum and copper chloride? Yeah, go ahead and get that for me if you can. All right, so here are the things that we're swapping. Swap. And only one of them is a compound, so this is a single replacement. That's supposed to be the letter M. So a single replacement means that you are replacing one thing for another, and only one of those is a compound. If it was a double replacement, that would be something like this. Where I would swap these two. And this equation is imbalanced. But that's okay. So I would swap the position of magnesium and sodium. This would be a double replacement. So you can tell if something is a single replacement or a double replacement based on the number of compounds there are in there. So here there's one compound, but here there's two. Okay. Yeah, now we have that balanced equation. We can do that problem. So I'm going to go back up here and erase. All right, so let's see here. So there's my equation. Let me just move this over. And I have 35.8 grams of whatever the hell this is. I don't know. Acetonitrile, maybe? I don't know. All right, so what I need to do is, so first I have grams of this. What is the question asking me for? How many grams of CO are produced? Okay, so whenever you have grams of something, turn into moles when you're doing these stoichiometry problems. And so what do we do here? Well, if I need to know the number of grams in a mole of something, I would go look that up on Lentech. So let me get the Lentech. I don't need this text anymore, so L for Lentech. C2H3N is 41.05. So 1 mole of this equals 45.01 grams of it. And then I know the number of moles of the first thing and the moles of the second thing because I have this balanced equation up here, right? So for every 4 moles of C2H3N I use, I also get out 8 moles of carbon monoxide. And then finally down here, 1 mole of carbon monoxide is CO, 28.01 grams. So we're going to just pull this down here. And so now we'll do the... Oh, that's weird. So working now? Yeah, there we go. Okay, so now we'll do the dimensional analysis. So we'll turn grams of this into moles of this. And then we'll turn moles of C2H3N into moles of carbon monoxide. And And then we'll turn moles of carbon monoxide into grams of carbon monoxide. All right, so we'll write all the things in, and 1 mole of whatever the heck this is, 45.01 grams, 4 to 8 ratio for the balanced chemical equation, and then 1 gram of, or 1 mole of carbon monoxide is 28.01 grams. And when I did that, I got 44.6 grams of carbon monoxide. All right. So for the next question about the solution. So if I put 50 grams of sodium nitrate at 40 degrees Celsius into water, and this is true, and then all I do is change the solution condition to this, remember that for all of our solutions that we looked at, they all tended to do something like this, right? So, as temperature increased, solubility also increased. So if my solution increases in temperature, so let's say this is 40, and this is 70, what will the solution be? Well, at 70 degrees, it can hold more stuff in there, right? You can add more solid. So if it's at 70 and there is more solid that can be dissolved in there, the solution must be unsaturated. And it looks like you're at 75 degrees, but whatever, it's the same thing. So solutions, when you heat a solution, it tends to become unsaturated because you can dissolve more stuff in a hotter solution. If you cool stuff down, they tend to be become saturated or supersaturated depending on the circumstances. All right. Check the following that will mix together. So for the mixing one, remember that the entirety of the solubility chapter revolves around like dissolves like. And so that means polar plus polar mix, and so do nonpolar plus nonpolar. And so you need to look and see what are the intermolecular forces that are present. So we know that if you have only C's and H's, you get nonpolar. Because we've mentioned that several times. The other ones you could draw the Lewis structure for. So for instance, methanol is just this. And you should be able to draw that and look at that and go, oh, that's going to be polar because of the CO bond and the OH bond and how the geometry works out, right? So this is polar. But methanol is paired with pentane, and pentane is all C's and H's. So pentane is nonpolar. So methanol and pentane should not make a homogeneous solution. So methanol is polar, but pentane is nonpolar. So this will not make a solution. Hexane and toluene are both just C's and H's. So hexane is nonpolar. Toluene is nonpolar. Hooray, that'll make a solution. With water and benzene, again, benzene nonpolar. Water's definitely polar. Won't make a solution. But water and formaldehyde, water is definitely polar. If you don't know what formaldehyde is, draw its Lewis structure or look it up online, right? This is very clearly polar in this direction. And so they will form a solution. What do we need to know about dispersion forces? Everything about dispersion forces, right? So, know when dispersion forces are significant, so they're more powerful as molar mass increases. So as the molecule gets bigger, dispersion forces get stronger. They are the weakest intermolecular force for a small molecule, so know that too. And know the trends on things like how shape is affected. So a molecule that's long and has a high surface area has stronger intermolecular forces for dispersion than one that's spherical. Oh, excuse me. All right. What mass of carbon dioxide is contained in the headspace of a soda bottle? So let's draw a picture of that. So here's my soda bottle here here's the lid, and it's got the funky Pac-Man ghost bottom on it. And so inside the bottle, that wasn't a very good line, was it? There we go. Inside the bottle is a headspace. So the headspace is this right here. And there's CO2 in there. And so we know that the volume of the headspace is 158 milliliters. The pressure is 2.56 atm, which is why when you open your soda, it goes because all the soda is coming out of the bottle and not going into it because it's pressurized, right? And the refrigerator is set to keep the contents at 2.68 degrees Celsius. Okay. So what mass is in there? Well, first of all, what equation do you think you're going to use? You only have a before condition, right? There's no after. So we're going to be using the ideal gas law. Secondly, you're solving for mass, right? What variable will get you towards mass? Well, moles will, since you know it's CO2. So we're going to solve for N. So let's do that. So N equals PV over RT. Because I just divide both sides by RT. And we'll just plug in all these numbers, but we do need to make them match up with the constant. Remember that the ideal gas constant looks like that. If you aren't writing out the units and doing this the same way, though, every time, like, shooting yourself in the foot. So make sure that you have everything in these units. If you just times all these numbers together, you'll get it wrong. So first we need so we need pressure, which is in atmospheres. So we could just take that number as is. And then we need volume, but volume's got to be in liters, right? So we'll just change this to liters. Because there's 1/1000th of a liter in a milliliter. So we just divide by 1,000. R is the ideal gas constant, so we just write that in. Yes, you should write it every time. And then T needs to be in Kelvin. So what is 2.68 in Kelvin? 2.68 plus 273.15 is 275.83 Kelvin. And then you can check to make sure all of your units cancel out, which all of them but moles should for this problem. And what gas are we working with? This is CO2, so we'll write that here. I made a typo. There we go. Divided by 0.08206. 0.83. And I got an answer of 0.0179 moles of carbon dioxide. So this is the number of moles of CO2 in that headspace. And so you can convert this into grams of CO2 by using the molar mass, and we should all know how to do that. We're going to times it by the number of grams per mole, which once you've done that, should be this. Okay, so next question, which liquid has the highest vapor pressure? So remember, vapor pressure is linked to intermolecular forces. So we'll go up here. I'll just hit clear again, I guess. So something has a high vapor pressure if it has weak intermolecular forces. And something has a low vapor pressure if it has strong intermolecular forces. And this is because of how strongly the molecules stick to each other, right? If I have strong forces, my molecules won't want to escape and become a vapor. They want to stay attracted to each other. If they have weak intermolecular forces, then they all escape and they become a vapor, and the vapor pressure is high. And remember that vapor pressure is also linked to boiling, where if I have a low vapor pressure, I have a high boiling point. And if I have a high vapor pressure, I have a low boiling point. So you have to look at those molecules and figure out which one has the highest vapor pressure. And so you would just write them down. And then you have to organize them by what types of intermolecular forces there are. Well, if you draw out the Lewis structure for CH2O, which we did earlier, you would see that it has dipole-dipole. Water can hydrogen bond because it's water. And then pentane just has dispersion. Of these, we want to be looking for the one that has the highest vapor pressure. So we want the one that has the weakest intermolecular force, which is this one. Because dispersion forces are weaker than dipole-dipole or hydrogen bonds. For the next one, you have a piston with gas in it. And you can see very clearly that this is a before and after problem. So, because it's listing things and then you do the action and it changes, right? So we have pressure, volume, and temperature, and then we have before and then after. So make a chart. So I have a piston, which contains a gas. Here's my gas right here. Do, 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 do. And we're going to take the piston, we're going to compress it so that the volume is reduced. So here's what's going on in our picture here. So this went down. So let's write down all the initial things. So the initial temperature is 10.3 degrees Celsius. Initially, its pressure is 1.13 atm, and its volume is 1.10 liters. And I want the temperature of the mixture after. If the pressure is then 4.03 atm, and its volume is 0.435 liters. So how do I do this? Well, if I write out the formula, we're going to solve for T2, right? So unfortunately, that's on the bottom of the expression. So I need to get that to the top by multiplying both sides by T2. So I got to do this first, so that these cancel. We get this on top. And then I need to isolate T2. So I can multiply both sides by T1 and divide both sides by P1V1. So you should get something that looks like this. Right, because I multiply both sides to get this up there, and then I divide both sides to get this down there. And now we can just punch in our numbers, but you can't use Celsius in gas law problems, right? You have to turn it into Kelvin. So we cannot enter this number as written. So let's turn that into Kelvin. And I get 283.5. Now, what that means is that our answer is going to be in Kelvin when we're done. So we'll need to turn it back into Celsius. But that's totally okay. We can do that. I don't know what any of these numbers are. So pressure 2 was 4.03. Volume 2 was 0.435. Temperature 1, 283.5 Kelvin. Pressure initial 1.13 atmospheres. Volume initial 1.10 liters. All the units cancel out. And when I'm done doing that, I punch it all in my calculator, and what do I get? I got 399.8 Kelvin. Which we can turn into degrees Celsius by subtracting 273.2. I actually only need to have 3 sig figs, so this would be 400 Kelvin. And this would be 127. There you go. Do you need to know how to draw electron configuration diagrams for the final? Have you done that at all in this class? Why would I test you on the final on something we've never covered? I mean, I'm trying not to be an asshole, but that, That would definitely make me an asshole if I did that. So, no, we do not do electron configuration diagrams. Is the substance binary, ionic, polyatomic, or covalent? Remember that covalent compounds are nonmetals only, and ionic compounds are metals. So in those compounds listed there, so you got CH4, K2O, and NaNO3. There are no non-metal, or sorry, there are no metals in this, so this must be molecular or covalent. Not sure which one it lists it as, but they're the same thing. Here I have a metal, so this is ionic. And because there are two different elements, it becomes binary ionic. And then here I have a polyatomic ion, so this is a polyatomic ion. So for polyatomic, look for polyatomic ions. There's that list of polyatomic ions that I asked you to learn at some point in the class. I don't remember what chapter it is anymore. Probably chapter 3 or 4. All right. That looks like all the questions that were asked. So I'm going to, let's see here. It's only been like 30 minutes. So I'm just going to turn the music back on here. And I'll wait for more questions and we'll see where we go from there. So let me do that real quick. And I'll see you in about 2 or 3 minutes. So go ahead and keep posting questions. All right. Do. It's so catchy. Oh, excuse me, I had to cough there. Okay, so we'll scroll back up here and hit clear. So what is the molarity of a solution when 11.6 milliliters of 4.65 molar sodium hydroxide are diluted to a final volume of 200 milliliters? Okay, so remember that the formula for molarity is, let's get a different color. This one. And so for this problem, we have the stock solution was 4.65 moles per liter. And I have 11.6 milliliters of it. And then when I dilute it, the final volume will be 200 milliliters. And I need to figure out its concentration. So we're going to solve for the concentration of the dilute solution. So we'll solve for that. We're just going to divide this guy over here. And then we'll punch in the numbers. So 4.65 moles per liter times the stock solution was 11.6 milliliters. And the dilute volume was 200 milliliters. And you'll notice that the volume units cancel out, so I will end up with molarity. And my concentration that I calculate is that. So just like the problems we did in class for that section, but I made you solve for a different variable. And then for the sucrose solution down there, remember that the formula for mass volume percent is mass solute over volume of solution times 100%. And so the mass has to be in grams and the volume has to be in milliliters to do this. So that means that we had 58.3 grams of glucose in enough water to give 608.2 milliliters of solution. And so when I do that, 58.3 over 608.2 times 100, I get 9.59% MV. All right, those are the only questions that I got, so we're going to take a break. I'm going to put the break card up for 10 minutes, and if there's any more questions, let me know. Otherwise, we'll call it a day after the break is over, and we'll talk a little bit about stuff, I guess, like administrivia, like what's left to talk about, really, at this point. So let me reset this. Boop. And you get to listen to the internet settings music on the 3DS for 10 more minutes. Type in any questions that you might have in the chat, and we'll go over them after the break. See you in a bit. Alright, we're back. Let's get rid of this. Alright, so I see a few more questions in here. Regarding the rotations on a wheel, I don't know that problem off the top of my head. Like, I would need to see the problem in order to solve it. Let's see here. So we're going to make a solution out of 0.450 grams of NaCl and enough water to make 100 milliliters of solution. And so we get this solution. Now, you do need to know that for sodium chloride, a 0.9% MV solution is isotonic with cells. So what that means is that if you put 0.9% solution, your cells will get the proper hydration level they need, and you won't put too much water in them or take water out, for example. So what that means is that our solution right here is too low. So this would be hypotonic. And what that means is that for our cells, there are lots of ions in the cells, but relatively outside there are not as many. So water is going to move into the cells. Because what does water do? It moves from a concentration that's low to a concentration that's high, so it can equalize them. So our answer must include water moves into the cells. And then, what is the process during which water moves into the cells? Well, if you go and look up what that is called hemolysis. So you'll notice that two of the options say water will move into the cells, but one of them says hemolysis will occur, or hemolysis, and the other one says crenation. Crenation is when they dehydrate. Hemolysis is when they burst because they have too much water. So this would be the correct answer, which looks like it would be option 1 for this case. I think that was the only question that was asked, actually. So, yeah. If there aren't any more questions, this will be last call for questions then. I'll go turn the music back on then. Oh, I looked back and there's a question there, so okay, let me turn this down again. So we'll answer that. So we know how far or how long the person drives for. They drove this many minutes. And you know that they are driving at a certain speed of miles per hour. So if I can turn this into hours, then I know how many miles they went. And then I can convert to a distance. So let's do that. So we turn minutes into hours. Hours can be turned into miles based on the speed that was given. And then you could just do dimensional analysis to turn all of these things into each other. I'm going to erase this because we don't really need it anymore. So miles, feet, inches, centimeters. And so we just do a bunch of conversions now. So there's 60 minutes per hour. We were traveling 56.2 miles per hour. In a mile, there are 5,280 feet. In a feet, there are 12 inches. And in an inch, there are that many centimeters. And so I get a huge number of centimeters. 36 centimeters. There we go. So I get a big distance. And that makes sense because they went nearly 50 miles, right? So there should be a lot of centimeters in that. All right, last call for questions. Pardon me while I yawn some more. All right, well, if it looks like there aren't any more questions, then I'm going to call it a day here. So we'll go back over to here. I do want to thank everybody for coming out to the lecture. And yeah, that's it. So there is a lab worksheet due tomorrow. Make sure that you get that in by the deadline. If you absolutely need to take the extra day, you can turn it in on Thursday. That'll be last call. All NQA stuff needs to be done by Friday this week. So absolutely have to get everything into me by Friday. Anything you may have NQA'd for, like, take the quiz later, whatever. Friday is the absolute last day. If you don't do by then, it won't be counted. And then I will grade everything else over the weekend and hopefully get grades done by Tuesday when they're due. So, yeah, there isn't really much else to say other than best of luck on the final exam. And enjoy your summer once you're finished, because it's just around the corner. Yeah, I don't got anything else. Have a wonderful summer break, and take care.